All right. So there's some reactions that we've done before that will serve as like a good segue into chapter 15. So the generic name for chapter 15 is conjugated systems. But we're going to do some extra fancy stuff eventually related probably to ultraviolet spectroscopy and a world famous reaction known as the Diels-Alder reaction. So on the simpler side of things, we've learned that you could take something like this alkene, and if you take that alkene and you treat it with a high concentration of Br2, usually at low temperature. RT means room temperature or below. So that's, reacted fairly cold. Okay. And what else about this now? This would probably be favored if you were to use a solvent for this. It would probably be favored if you had some kind of a polar solvent. I'm going to add that in parentheses because I'm going to think of that as kind of hypothetical, because I would have to try to figure out what polar solvent could I use that wouldn't interfere with the reaction. So under these conditions, what does an alkene do when you react it with Br2 typically?
It's anti-addition.
Yeah, you get anti-addition of Br, of the bromine, right? So we form a bromonium ion like we did before. And so net result is Br added anti. Let's see, to show that. So you probably get this compound and its stereoisomer, enantiomer. So this one we got back. So we could have gotten those two stereoisomers, which to me look like enantiomers, right? If we did this reaction. Okay. Now, we also learned a way to do something else, which would be to leave the alkene double bond intact, but instead put a bromine in that position. And what reagent system did we learn would do that? You should see Allison's face every time I ask one of these questions that she thinks you should know. What's the reagent system that would put the BR in that position?
Yes.
What else?
Like, triangle.
So NBS in carbon tetrachloride in the presence of either heat or light. In describing it in this way, what NBS does for a living, it delivers a low concentration of Br2. You're using heat or light, which are conditions that will allow for radicals to form. So if it's conditions that will allow for radicals to form, and the bromine is being released into the system in very low concentration, then what will happen is the radical that you're most likely to produce in this case would be the radical that's most stable, right? So we could think of forming some kind of radical here or here, but the one that's most stable would be what we would refer to here as our allylic or allylic radical. There are some Jamaicanisms that I've chosen to leave behind. So as an intermediate, what you go through in this reaction is that kind of radical, an allylic radical. And that radical is extra stable because of what? I don't want to use that word yet. Why would I say that radical is stable? Okay. Right. Because we can write an alternative resonance structure of it. Right? Single electron transfers now.